In the last lecture, we have discussed about revised simplex method with an example. So in this lecture, we'll also discuss the revised simplex method with another example so that it becomes clear to you. So let's start. We'll start with the problem as given in the screen here. So we have to maximize z subjected to two constraints x1, 3x1 plus 4x2 less than equal to 6 and 6x1 plus x2 less than equal to 3 and x1 and x2 greater than equal to 0. So this we'll have to express in canonical form, and it can be expressed in this manner. And first we'll solve it by the conventional method, and then we'll again solve it by the revised simplex method, and then we'll compare it so that it is easy for you to understand. So this is the conventional solution. You can take a screenshot of it and keep it in front of you while I'll discuss the method by revised simplex method, and you can check the values. Particularly you should be interested in these values 9/2, sorry, this, yes, I'm new with this pen, so please bear with me. Okay, so you should be interested in this. You should be interested in these values. You should be interested in these values and these values. Okay, so let's start with the revised simplex method. So I'll be storing the values of the column matrix in P1, P2, P3, P4. These are all Aij values of x1, x2, x3, x4 in the constraint equations, and b is equal to 6, 3. That we know. So here we'll start with iteration 1. Iteration 1, as we start in conventional problems, here also we'll be doing the same thing. We'll start with x1, x2 is equal to 0 and x3 equal to 6 equal to 6 and x4 equal to 3. We'll start with this solution, and obviously z will be 0 in this case, and we'll check whether this solution is optimal or not. Obviously this will not be an optimal solution. So if this is not an optimal solution, what will be, we'll iterate towards an optimal solution. We'll iterate, and again we'll check that in the next iteration whether that is an optimal solution or not. If that is an optimal solution, we'll stop there. If not, then again we'll iterate, and again we'll check whether that is an optimal solution. So these steps keep on going until we'll find an optimal solution. So start with iteration where will x3 and x4 are the basic variables, and therefore xb is equal to x3 column matrix x3 x4 equal to 6, 3. That means x3 is equal to 6 and x4 is equal to 3. So this is the solution with which we are starting, and this is my initial basic physical solution, and we'll check whether this is an optimal solution or not. To check this, we require to find out b. B is basically a column matrix of P3, P4. In this case it will be 1, 0, 0, 1, which is equal to B inverse. So it's an identity matrix, so B inverse is this, and also we require to find out the CB in order to find out Cj minus Zj. So CB in this case is a row matrix 0, 0. We have taken intentionally row matrix while other being column matrix. Okay, CB is 0, 0 because the coefficient of x3 in objective function is 0 and coefficient of x4 in objective function is 0. So we'll find out y is equal to CB, B inverse. So B inverse is basically identity matrix, so C equal to CB. So y will be equal to 0 0, and therefore C1 Z1 will be equal to 2, and C2 Z2, it will be Z2 bar will be equal to 1. So therefore these are positive value. This is an optimum solution, and this being the highest value, so therefore this will be the entering variable. X1 will be the entering variable, the non-basic variable. Currently it will become a basic variable, and to find out which variable will be exiting, we have to find out P1. So P1 will find out, P1 is equal to P1 bar, in fact we have to find out. So P1 bar is equal to P inverse P1 equal to P1 equal to 3 by 3, 3 by 6. So this was initial solution was, I think we have started with 6 3, so minus 3 theta, and this minus 6 theta greater than equal to 0, greater than equal to 0. So this gives the theta is equal to 3. Sorry, theta is equal to half. Theta is equal to half. So from which equation? From this equation. So x4 is the exiting variable and x1 is the entering variable, and column 1 is the pivot column. So with this we move on to the next iteration. So next iteration, xb will be equal to x3 x1, which is equal to half. So 6 minus 3 by half will be equal to like this. This will give us 12 minus 3 is 9 by 2 and half. So this is the starting of my next solution. This is exactly what has been done here. So it is 9 by 2 and half. So this is the starting of my next solution. Now I'll check whether this solution is optimal or not. To check this optimal or not, what is required to find out? We require to find out B, and B is what? B is equal to P3 P1. Okay, so P3 P1 is equal to 1 0, and what is P1? P1 is 3 6. So B inverse will be equal to 1 by 6 minus 0 is equal to 6 1 minus 3 0. So this gives us 1 minus half 0 minus 1 by 6. So you can check this value with a conventional solution in the next table. B inverse should match. So now I am interested in finding out CB. CB will be equal to 0 and the coefficient of x1 in the objective functions, which is 2. So xb is equal to 2. So CB B inverse, so this into this will be equal to 0, and this into this will be equal to 0 into half plus this, it will give you 1 by 3. So y becomes 1 by 3. So now with this y value we can find out the Cj minus Zj. Cj minus Zj comes out to be C4 minus Z4, which is a non-basic variable. Therefore we are finding out C4 minus Z4, which is equal to minus 1 by 3, and C2 minus Z2 bar, which comes out to be 2 by 3. Now this value is a positive value and therefore it is not optimum. So this will be my entering variable. This will be my entering variable, and P2 will be my pivot column. So P2 bar will be finding out. So we'll find out P2 bar like this, and we'll find out the theta. So theta comes out to be 9 by 7. Theta comes out to be 9 by 7 here. So accordingly we'll find out in the next iteration, we'll find out the xb. So it comes out to be 9 by 7 and 2 by 7. So this is my solution, current solution. X2 is equal to 9 by 7 and x1 is equal to 2 by 7. You can check in the conventional solution table. This is the solution of the third table, and therefore the basis will be P2 P1, which is comes out to be 4 1 3 6. 24 minus 3 is equal to 21. 1 by 21, that's 1 by 21. 6 minus 3 minus 1 4. So these two are interchange and this minus is added, so it comes out to be this. You can check this, you can match it with the conventional solution. In the third table it should be matching. So here again we will find out CB. CB is required. CB is the coefficient of x2 and x1. It is 1 and 2. Therefore y we have to find out. CB V inverse. So y comes out to be this value. So once we have y, we need to find out C3 minus Z3 bar and C4 minus Z4 bar. So this two, if comes out to be less than 0, then it will be an optimal solution. So it is coming out to negative, and this also negative. This is the optimal solution, and the solution is x2 is equal to 9 by 7. That is the initial solution with 3 step in this step, and z comes out to be 3 by 7. So this is how you solve the linear programming problem using revised simplex method. So I hope watching these two lectures on the revised simplex method, this particular method is clear to you. If any doubt is there, you can write to me and I will try to get it clear. Thank you for watching this video.